Good morning, you wonderful Earth Science kids. Sitting here on a beautiful snowy morning. What a great time to talk about erosion. All right. Erosion, after we weather rock, after we have either physically or chemically weathered rock, what do we have? We have the remnants of that, sand or clay, something like that, coming off the rock. It might just be big chunks that have fallen off the rock. They're just going to stay there, right? Well, maybe not. What's the Earth going to do with them? Earth might just take all that stuff away. So erosion is the transport and removal of sediments, any rock fragments, by water, wind, or ice. Those are the major, what we would call the agents of erosion, those things that do the hard work of erosion. All of it is basically powered by gravity. If you have a landslide, that would be gravity alone, but water is being pulled downhill by gravity. Wind, well, fundamentally, wind is really powered by gravity, and it's because the density differences that cause it, and that's gravity powered. And ice, of course, is pulled downhill just like water is. So we look at erosion. It breaks up into a few different categories, what we would call agents of erosion. Yes? So we would have the first, gravity alone, wind, running water, or glaciers. These are the four agents of erosion. Gravity acting alone, you could debate whether that's actually an agent of erosion, but certainly powers it. Gravity by itself. Look at all these things that gravity does. Slump and creep are sort of a mountain's way of slowly moving down. If you think about, I walk through roads in the woods sometimes, long abandoned roads, and many of them, if they're on a hillside, they're only like this wide. Now, before I ever understood about stuff like that when I was a kid walking on those roads, I would wonder, who made these roads? These are stupid roads. You can't pull a horse and wagon on these roads. And then learning what really happens, if you think about a hillside and it freezes, when it freezes, the hill is pushed up a little bit. When it thaws, does it go back the way it came? No, it just gets pulled down by gravity. So the whole hillside freezes and thaws, freezes and thaws. And so hills are very slowly creeping down, right? Sometimes whole mountains collapse in mudslides. Sometimes the ground gets so wet, it is so thick and a big slurry, and that will pour down in a terrible mud flow. Mud flows are one of the most dangerous things. While you might be able to get out of water sometimes, mud is much more difficult. Mud flows are truly dangerous. These are all termed as mass movements. If we think about wind, what does wind do? Well, wind does a couple things. Wind does abrasion, right? If you walk on the beach on a windy day, you're not going to do that for long because the wind is picking up sand and it's hurling the sand into your legs. It hurts. That would be abrasion. If you think about a rock in that rock constantly getting wind blown will smooth and polish it quite nicely. The other thing it would do, think of a desert where there's no vegetation holding anything in. And then think of a really windy day. As that wind comes along the valley floor, what you're going to see endlessly is big clouds of dust. How big are those particles? Tiny, tiny particles. Does it pick up the pebbles? No. Does it pick up the sand? Not really. It picks up the silt and particles finer than that. So it takes the finest particles away, leaving the larger particles. That is known as deflation. Right? Deflation. You're removing all the small particles, just leaving the larger particles. That really governs what a lot of deserts look like. Running water we'll talk about. And glaciers, there are two kinds of glaciers. The continental glaciers. Where do you find continental glaciers? About Antarctica, entirely covered by a continental glacier. Valley glaciers probably should more be termed mountain glaciers, but the mountains get so much more snow than can melt in the summertime that starts coming downhill. They turn all that compressed snow turns into ice, and that starts flowing downhill And they'll, of course, find their way into valleys and carve out the valleys. So valley glaciers as well there. So that's basically erosion, the broad idea of erosion. Let's talk about running water for a second. When we're talking about running water, we define the areas that are serviced by a river as a watershed. In other words, all the water that falls in that area, if it makes its way down to a particular river, we would call that a whole watershed of that river. It's a drainage basin of the river. In between watersheds, you would have a line, and the fun idea, it doesn't work, but the fun idea is if you were to pour a cup of water on that line, half of it would go into one river, half of it would go into the other river. Of course, probably all of it will evaporate. So this is kind of what it looks like in New York State. So you can see the watersheds are, you can circle around a watershed by just following the divides, right? So everything here drains into this river here. These things here drain into that. Over here drains into that. So if you draw around this whole thing and say you're just talking about this stream here, all right, well, then you're naming a larger watershed. If you talk the Catskill Creek, that's a pretty big watershed. But if you talk about the Delaware River, that's a huge watershed. Okay, that would be a divide, the high area between two watersheds.
So these are the major watersheds of New York State. And you can see, well, which watershed are we part of? When you look and you find Sullivan County right here. That watershed obviously is in the Delaware River watershed, except for a few extreme eastern parts, which would be in the lower Hudson River watershed. And you can see there are different watersheds all over New York State. There are 4 ways streams move sediments. So the first is to just dissolve the things that are there. For example, salt would be dissolved into the streams. Many streams have a little bit of salt in them. You can't taste it. It tastes like fresh water. But if that salt gets into the ocean, when it evaporates or when the water evaporates, it leaves the salt behind. That's why the oceans become increasingly salty. Suspension. Now, particles are suspended in moving water. Most of the time, though, when I look at water in a stream, it's clear. So very few particles are being held in it. When does the water get filled with particles? Obviously, when it's flooding. That has a lot of ability to carry many particles, even fairly large particles. Some things float in water because they're less dense. Typically, that's organic stuff. So organic stuff will be floating down the water. Well, look at that. Is that stream flooding? Sure. You could see a lot of the trees on the edge of it clearly in the water, so the stream must be flooding there. And you can see that's not clear water either. So solution, suspension, and flotation all move particles at the same speed as the water. Traction. Along the bottom of a stream or river, you have big rocks. Those usually stay there again until it's flooding. When it's flooding, they can be rolled along the bottom. So they do not move at the speed of the stream at all, but they are slowly moved downstream. So when you look at this now, you could see all these rocks here. Now, they might stay there for months and months and months. You'll see them. Sometimes if they're really big, you'll see them for some years. But then there'll be a tremendous flood, and you come back and look, and everything's different. All these rocks have been moved. Now, you know they can't be moved upstream, so they are slowly working their way downstream. And of course, as they work their way downstream, they get all beaten up and broken down into smaller particles. In moist climates, running water is going to be the chief agent of erosion. The size of the particle carried depends on the speed of the running water. Faster water can carry large particles. Slow water cannot carry large particles at all. And if you look at this, it's on your reference tables. And this graph, look at the two sides. You have the particle diameter on the y-axis and the stream velocity on the x-axis. This is on page 6 in your reference tables. And it's a wonderful chart. And it allows us to ask all sorts of questions, like what's the largest size that can be moved by 200 centimeters per second water? So that's stream velocity. If that's 100 centimeters, that line here must be 200. So, and you see another line right up here. So if we look down, so where does it cross that line? Right here. So what's the largest size? If you read over, so that would be cobbles. If a river can carry a cobble, what other particles can it carry? And I hope you realize it could carry all the smaller particles. So if a river is moving at only 1 centimeter per second, what's the largest particle that could carry? So read up from 1, and you clearly are in sand. And then it could carry all the particles smaller than sand as well. So that's how you read that chart. Well, humid landscapes, you can tell this is what we see out our window. And if you're, say, visiting the Grand Canyon or areas out west, you'll see stuff like that. What I'd like you to see is this. The geology underneath can be absolutely identical. So it's not what the rock is under us that causes these formations. I mean, it has something to do with it, but we have the same type of rock that the Grand Canyon has, basically. But why don't we have stuff like the Grand Canyon? Well, think of it. When it rains on our hills, there's vegetation there. It doesn't let the sediments just be carried away. The roots bind everything together. So the root systems in the vegetation turns out to be extremely important to what our mountains look like. What's going to determine the speed of a stream? Well, two things. The discharge, the amount of water. When it floods, it goes faster. And down a steep slope, again, it goes faster. When a river is going in a very flat area, the river goes very, very slowly. You can see here is a river moving along quite quickly. And now you can see some things perhaps you couldn't see before. Where did all the sediment here come from? Hey, did that come from over here and roll across the river and get here like that? No way. This sediment all came from upstream because the river carried it downstream, right? And when the river was flooding, it was much higher than this, and it dropped the sediment there, slowly bringing that sediment downstream. Hey, take a look at this. Take a look at that rock there. How fast does the river have to move at some point to carry a chunk that big? Well, it rolled it along the bottom, but that river moves very quickly. And this would be a river going or a stream going down a steep slope. Also, if you look at that rock there, this could carry pretty big sediments. So how fast can water go? Well, it's always a balance. Gravity's pulling it down, but friction with the stream bed holds it back. Streams are slow near the bottom and sides and fast in the top middle. Right? If you're wandering out into the Delaware River, you know you could go a few feet out in it, usually if it's shallow, and the current is not going very fast. As you get further into the river and it starts getting deeper, it certainly starts getting faster. Now, when a river goes around a bend, the water is trying to go in a straight line. So the water goes to the outside of the bend and then is curved by that bend. So the water is going fast on the outside of a curve. Erosion is occurring here. Well, that means water is going slowly on the inside of a curve. And what's the opposite of erosion? Deposition. So here's a stream, and you can see the maximum velocity right in the center, and on the sides of it, it would be much slower. Saying the same thing. These arrows are showing where the stream is going fastest. So fastest at the top, middle. Important diagram. Look at this. Deposition is always occurring here. Why? That's on the inside of a curve. If the water's going slow here, it's going to deposit. If the water's going fast here, it's going to erode. Think about that. This river bend then is actually moving that way. This river bend is moving that way. So over long periods of time, and this usually happens very much on a flood, the river actually changes its course. So if you look where the river is going straight, A to B, look at the cross section you'd have. It's just deepest in the middle. But where the river's going around a turn, it's deepest at D here rather. D then would have a very steep bank going into steep water or deep water, and C would have a very shallow bank. All right, can you say where the river would be going fastest? So let's find a place where the river is going fastest. Outside of the curve, outside of the curve, outside of the curve. The river is going fastest on the outside of any curve. Where's the river going slowest? Well, how about here? On the inside of a curve, on the inside of a curve. So I've learned when I'm paddling on a river, that's really handy to know where the water's going fast, where the water's going slow. If I want to take my boat out of the water, I need to find a nice shallow bank. That would be the inside of a curve, almost always. Here's a satellite photo. You can see, same thing. On the outside of the curve, the water is going very fast. And on the inside of the curve, the water is going so slow it deposits a great deal of material. And that is universal. That means that this river is heading that way. And this continues on every river, and it makes a river sort of a living thing. It moves constantly in its channel. The bedrock structure will affect the stream drainage patterns. Around here, where the land is just gently sloped, we would call it a dendritic pattern. So if you fly over it and you see a dendritic pattern, you have a basic understanding of the bedrock geology. What happens if you see an area where all the rivers are radiating, or all the streams are radiating away from a central point? Well, look at that. It has to be a hill. Everything is going away from the hill. If you see this bizarre pattern happening here, well, there must be some like faulted bedrock structure that is keeping the rivers in a particular channel. And if you see some combination of faulting and the radial flow, that would be like this. And look at the bedrock structure here. It's a combination of rivers and these faulted geologic structures that force the water to go. So it gives you an endless idea of how this works, the bedrock structure, just looking at the streams. So the Catskills. Catskills, any place you see horizontal bedrock, around us anyway, you know you're in the Catskill Mountains. The Catskill Mountains aren't even really mountains. It is a plateau. It is a flat chunk of rock that was lifted about a mile into the air. And after that, then, the stream started cutting down. So it's really the Catskill Valleys. This huge flat piece lifted in the air, and the valleys have been cutting it down. That's what made the Catskills. Notice the Grand Canyon, the same sort of thing. Look at nice horizontal layers. You can see that if you know what you're looking for. So the Grand Canyon is also a plateau. In some areas, erosion by wind becomes the dominant force. So wind will pick up loose material and carry it away. This will look mainly in dry areas. There's nothing holding down the soil, so when the wind comes along, it picks it up and moves that. So the wind, the sand in the wind will abrade the rock, will gently cut the rock and shape them into something called ventifacts. Look at that. This is in the dry areas in Antarctica. Most of Antarctica is covered by this continental glacier, but there's a few dry valleys where the glacier is not there. And the only thing ever happening, there's no water ever in Antarctica, not liquid water anyway. What is shaping everything is endless wind, and sometimes really hard blowing wind. And you can see these bizarre shapes. Sometimes gravity acts alone to erode stuff. If you have a mountain and part of it breaks loose and just falls down into the valley, that's just gravity. The particles are going to be angular and sharp. No rounding is going to occur. So here would be an example. You can see whatever rocks are above this are just breaking loose and falling down, mostly very angular and sharp rocks. Here's the side of Route 17 heading towards Middletown. And you can see, first of all, are we in the Catskills anymore? Well, are these horizontal beds here? I hope you can see that the bedding plane is all tilted like that. So we are certainly not in the Catskills anymore. But the point I'm using this for is this is gravity mostly breaking these particles off. Now, there's frost wedging and things like that, lifting the particles and starting to separate them from the parent rock, but then they just roll downhill under gravity. So gravity is acting as the erosive force here. All right, so erosion by ice. The bottom line is very simple. If you get more snow in the winter than can melt in the summer, you'll always have that snow. And year after year, it'll accumulate and grow into a large mass of ice, which can be pulled downhill by gravity. The large mass of moving ice is called a glacier. So when we look at this, check this out. This huge glacier is pouring down the side of Mount Robeson, the tallest mountain in Canada. Couple-day hike to get up here. And I'm standing on the edge of this lake, and once in a while I hear a thunderous roar, and I can't see anything. But then I'll see a little bit of dust or splashes coming up from near the edge of this glacier. All at once I realized these things here are like 120-foot tall pine trees. I wasn't seeing the glacier right. It seemed much closer than it actually was. This is about a quarter-mile thick of ice from here to here. And it calves off icebergs into this lake, which is appropriately called Berg Lake. And you can see the icebergs floating in this lake. This glacier is going to tear up the mountain. It's going to rip up the valley, deep in the valley, and make the valley very U-shaped. Think about where a stream cuts a valley. It's only in the center where the stream is. The rest of the valley has to weather out and become a V-shaped valley. With a glacier, every part of this ice is cutting the valley floor, so it makes it a U-shaped valley floor. Glaciers can move a vast amount of rock. Valleys, like I said, become U-shaped instead of V-shaped. Hills in New York have been rounded and bedrock has been polished. We had a special kind of glacier, not a mountain glacier like that or a valley glacier. We had a glacier that was a continental glacier come all the way from up north and just push over us and ride up and over mountains. And so all of our mountains aren't sharp, they're nice and smooth. Look at that. Can you see very clearly the U shape here? There was most definitely a glacier, a huge glacier there. This is up in the Canadian Rockies, and you see U-shaped valleys everywhere. What does that mean? It was glaciated. Glacial deposits. Well, glaciers pick stuff up, so it's got to drop it off. Sediments left by glaciers include all the standard sediments, right? But they're all mixed together. Why? Well, the glacier acts like a gigantic bulldozer. That doesn't separate sediments. What do you need to separate sediments? Yeah, water. Liquid water will separate sediments. So when a glacier is just bulldozing them in front of it, no separation of sizes. So it's a mess that's left by a glacier. And anytime you dig a hole in the ground here, you know about that because you'll be digging through soft sediments and immediately hit a huge rock. So where did our original soil go if that glacier came over here? Well, our original soil is gone. It's removed. It's to our south. The glacier carried it away. So look at that. It takes a second for this picture to pop into view, but again, we're in the deep Canadian Rockies, and if we look at this, here is the glacier. Look at this is where the glacier is pouring off the ice field, and the glacier is coming down this way. And actually, the ice is always moving down, but currently, the ice is melting at the front of the glacier much faster than the glacier is advancing. That's happening all over the planet. Anybody who knows anything goes, oh, look, global warming is changing how the planet is. A lot of people who know nothing say, oh, no, that's not happening. Science is pretty important. And when we're saying something like global warming, people should pay attention because your children, and in fact, you will notice the effects of it. These glaciers, how can you tell where they were? Well, look at this huge pile of debris. This huge pile of debris here. That was pushed fairly recently by that glacier behind it. So the glacier was up much, much higher. And we see this everywhere. The glaciers have been receding tremendously since the Industrial Revolution started, and they've been receding back really fast in more recent years. You still see glaciers pouring down these mountains. Glaciers continue, but as the world heats up, they will diminish tremendously in their size. Aside from that, though, look at the pile of debris the glacier has pushed up. Now, you can see huge rocks on that, and you can suspect that there's much tinier sediments there. In this case, the glacier acted just like a bulldozer and just pushed that. This is a side pile that the glacier pushed alongside of it. These piles of unsorted rock are known as moraines. So look at this. Along the edge where the glacier went about as far south as it could get, this is where we find these moraines. These big dark lines are the moraines you find here, and you find them all over the place. But basically, Long Island is a giant pile of glacier garbage that was pushed off of New York and Connecticut. Pretty cool. Without the glacier, you wouldn't have Long Island. All the structures on Long Island are leftover glacier debris. So when you see something like this huge rock sitting in the middle of the woods, how could that get there? In the olden days, people explained it as a tremendous flood with water moving so fast it could carry that stuff. What do you think of that explanation? Have you ever seen a stream, even in the worst flooding situation, able to carry a rock like that? Nope, nobody has. Streams can't carry rocks that big. They just can't move that fast. So scientists were left without an explanation till Louis Agassiz, a Swiss geologist, he watched what glaciers can do. Then he came to places where glaciers were not known about, and he told people, hey, see that? That's a thing carried by a glacier. Scientists poo-pooed the idea. No, glaciers were never here. But very quickly, as soon as they had that in their head, they started accumulating all sorts of evidence that certainly glaciers were here. On one of the trails I hike regularly, coming down the trail, the sediments on top of the bedrock have been eroded. I was coming down the trail one night, and the sun was setting, and it was casting light just across the rock on the trail, and I could see grooves of lines on the trail. Well, I took my compass out of my knapsack and put it up, and sure enough, the angle showed that these grooves were made, in fact, by the glacier itself, carrying particles and grinding the rock underneath it. The glaciers are covered with like rocks underneath them, so as the glacier moves forward, it'll cut these grooves, and the grooves are always about the same angle everywhere. So if you find them on a hill someplace, if you find a polished bedrock that the glacier had clearly carved, you'll see grooves. 50 miles away, you'll find some other grooves, and the angle is the same. I'll show you what that is. Oh, if the glacier has piled a big pushed a big pile of garbage in front of it, and then glacier melts back for a little bit, and then it surges forward, and it hits that pile, surges forward. It happens slow, but it still does it, and it hits that pile, and it mushes that pile. It rides up and over that pile, and it makes this, like, it looks like an upside-down canoe. These are called drumlins, and because the pile of glacier garbage is large, there's a bunch of them, and so geologists use the term swarm of drumlins. I just love that term, swarm of drumlins. Sounds like something out of, like, J.R.R. Tolkien. That shows you what happened here. So this huge ice sheet way up in Canada, so much snow fell down over thousands and thousands of years that it piled up many miles high. The gravity pulling it down makes it expand outward. You could think of it just like pouring out batter for a pancake in a fry pan. If the fry pan had little nicks and grooves on it, and you pour out a lot of batter in the center, will that batter come up and over the nicks and grooves? Sure, if it's thick enough in the center, it's pushing so hard, it'll come right up and over it. That's how this glacier could come up and over the Catskill Mountains. Had no problem doing that. 3 miles thick up in the center of it. It's about a mile thick here, but so much pressure from up north pushing it that it can come up and over anything. Pretty much everything in New York State had the glacier cover it. And you can see the dark line at the end shows how far the glacier got. So it didn't really get very far into New Jersey. It didn't really get into the southern states at all, but many northern states were completely covered by this glacier. New York was completely covered by it, but we're at the edge of the last glacial advance. So this is a good picture of what it is doing when you're at the front of a glacier. So here's the front of the glacier, and a glacier is always melting off. Even if the glacier is moving forward, there's still meltwater. I mean, certainly in the summertime, kind of diminishes in the wintertime. So this water then, all these sediments that the glacier has left, the water plays with, and it will sort out a lot of the sediments. So you see a lot of these things here. You see erratics. The water is not going to mess with erratics. It's just going to flow around them. Deltas deposited by the water at the edge of a glacier are called kames. Drumlins, of course, these swarms of drumlins here. Streams fill with debris, and the debris pushes the stream out of it, so the streams become what we would call a braided stream, choked with bedrock. Sometimes you'll have a stream running underneath a glacier. Now, if that's happening, it'll melt upwards. It'll do the exact opposite of what a stream does on land. With a glacier, it's easier to melt the ice above the land. So it makes this U shape going up. And that U-shaped debris, that U-shape is filled with debris, and it forms this object called an esker. It looks like a rock wall made by very strong, very drunken people who just threw the rocks together in this pile that sort of snakes its way around the valley floor. So there's a lot of neat glacial evidence if you know where to look. The effects of agents of erosion. Each agent of erosion leaves behind telltale signs that you could use to identify it. For example, a stream. It makes the particles rounded, right? Big or small, it makes them rounded. And we have so many streams around here, you know what they look like. Where would you find something that came from a glacier? Well, look in rock walls around here. All the rock walls that you see all over the place in the woods, in fields around here, those particles, all of them, those big rocks, they were left by glaciers. How can you tell? Well, are they really sharp and angular? No. Are they really rounded? No, they're somewhere in between. That's what a glacier does. Gravity alone, that's going to be really sharp and angular. You don't see any rounding or smoothing. Wind. Wind is the oddest of all because one side that was exposed to the wind gets all nice and smooth, and you turn the rock over and it's all very rough underneath it. So that would be an example of wind erosion. All right. So what clues tell how the pebbles were eroded? Look at the running water. Oh, so smooth. You can tell that's been bounced and smoothed under running water for years. Glacial ice? Well, glacial ice, it smoothed it a little bit, but it's still kind of angular. Again, think rock in rock walls. Wind is one of the odder ones because you turn the rock over, it's all rough, but the side exposed to the wind is nice and sometimes like polished, like glass almost. And a gravity fall would just be sharp and angular. So that's how you could tell which agent of erosion did the work of moving the particles. Hey, thank you so much for watching. I hope this helps. Bye-bye.